Alright, Metalhead Weatherman here. Hopefully you guys are doing well. We're getting on with this YouTube playlist that I had mentioned making a while back, where we can get more in depth with the weather on here. I could show you how to read forecast models and get a little bit more into the advanced stuff. So that way, if you wanted to follow along in mine or somebody else's videos that talks about weather, you will be able to do so easily. So we're continuing the whole forecast model, I guess crash course, if you want to call it that. I think I actually found the name for the channel and we just did it live on a video here. Weather Nerd Crash Course 101, I guess. Let me know what you think in the comments. But anyway, today we're talking about the severe weather parameters. I'm gonna show you guys how to read those on forecast models. We're gonna go over a recent event where a severe weather outbreak had occurred. It was November 4th. And then I'm going to show you how to find those forecast models and those parameters on one of the websites I use for forecast modeling. So we'll start out with the parameters, and this in the main key ingredients for severe weather, there's actually an acronym for it. It's called S.L.I.M, and you can see the letters right here and what they mean: shear, lift, instability, and moisture. We're going to start this out in order, of course, and arguably this is the first letter is probably the most important ingredient, and that's shear. Shear is basically turning of the winds with height within different levels of the atmosphere, and these can help maintain severe thunderstorms and help keep things organized. It's one of the more important ingredients, maybe not the most important ingredient. Kind of hard to say. Instability is just about as important, but we'll get into that in just a minute here. So one thing about wind shear that makes it really complicated is that there's actually two types of shear that you look for when it comes to severe weather development. We have speed shear, which we're going to talk about right now, and directional shear, which is coming up in just a second. So speed shear is simply as follows, because if you look at the definition of wind shear, it's turning of the winds. Speed shear is a variation of wind speeds at different levels, and what this will ultimately do is tilt these updrafts. And you're probably thinking, okay, well, what does tilting the updraft do for a thunderstorm? Here's a perfect diagram right here. So this is a thunderstorm with a non-tilted updraft. Rain falls in the center of the storm where the updraft is, and this will basically choke the storm off, because storms feed off of a collision of warm and cold air. It needs that warm air to flow into the storm to keep it breathing, and that cold air to help extend it out. When you have no shear, this won't happen. You just get rain, cool air coming out the storm, or outflow as it's called, and the storm ends up choking itself off. But in a sheared environment, that rain falls ahead of the updraft, and that warm air is able to sneak its way into the updraft, into the storm, and it can keep going for a lot longer. So it's always a battle between the inflow and outflow of the storm, warm and cold air. And that's really the key to everything. So speed shear is, and this is why part of why speed shear is important. Here's another reason why. Speed shear can create rotating air columns. Most of the time these are horizontal air columns, which is important because that's usually the first step that we will need to be looking for an environment that is capable of producing tornadoes with severe thunderstorms. The change in speed and height is important because towards the low levels we get that rotating column of air, and then it can be translated into vertical through that speed shear, and then eventually create tornadoes. Excuse me. I had something to drink, but I can't really burp for whatever reason. Apologize for that. Now here is directional shear here. So basically it's pretty self-explanatory. Directional shear is basically turning of the winds with height at different levels, and directions and directional is of course basically going to translate to the wind moving in different directions. So that, like, you can look at these little arrows here. This has the winds at the surface or the low levels moving at and the northwest. Then you have this moving towards the northwest here, the second arrow. Then you have this one moving to the northeast, and then northeast. So that directional shear is going to be key because it can help amplify that speed shear and usually increase a tornado threat here. You'll see more. We'll talk more about directional shear in a more intricate manner once we start talking about skew tees and hordeographs here, because that's the best way to kind of depict these. I have talked about that before though on some videos. You might see one of those videos in the top right corner here as well. But that's basically the start of us talking about wind shear. We're going to move on though to lift, which is really important, and there's 4 ways to do this. There's 4 ways to achieve lift, or atmospheric lift I should say. The most common way is this right here. It's a frontal boundary. We have cold air that is sinking and usually will be behind a cold front, of course, and then we'll have warm air out ahead of it. And of course we have a collision of the 2 air masses, and then we get thunderstorms that usually will form on the boundary. Then we have probably I would say the second most common instance, which would be convergence. This is where we get lift coming from the low pressure center. So we have these little inland cyclones like I've been talking about on the channel, and I'm even tracking one right now as I'm making this video. But it's always these little low pressure areas where we have to watch for the potential for some storms, for the lift to be achieved and some storms to fire off. You can almost look at atmospheric lift as almost like a trigger. So we often look for low pressure centers and frontal boundaries as a point of interest. However, orographic or the geography can also cause lift. There's plenty of times where we've heard of mountains creating lift in an atmosphere that was just lacking a little bit of a trigger, and we would still get severe storms. In fact, there have been plenty of tornadoes that have dropped on mountains. So I've heard some people say that they don't touch down on mountains. This is definitely not true. There have been plenty of pictures proving that. I think there was one picture of a violent tornado that formed above 10,000 feet and touched down on a mountain here. I think it was rated EF4. I'm not exactly which mountain that was exactly, but that just goes to show, don't always believe what you read from the tabloids. But there is one more instance as well, and this is convectional, and it's local heating. And this isn't as common, but it can happen. There's a few famous instances where this occurred. In fact, in my hometown or metro area, because I'm from Atlanta, the 2008 Atlanta tornado, there was a good instance of convectional heating right around the city, which allowed for that one tornado to form around our area. That was the only tornado warned storm that I remember at that time. Everything else that was going tornado warned, I think it was a little bit further off to the north or south, if I remember correctly. We didn't really have like a high chance of tornadoes. I think it was a 2% chance that was issued by the Storm Prediction Center. But that just goes to show you have to watch this one. You have to watch this type of local heating really closely. But it's also really hard to read sometimes too. So it can be a little bit messy here. But these are 4 types of lift here. It's extremely important to severe weather genesis here. So if I mention any of these 4 terms here, convergence, orographic, frontal, or convectional, pay attention because something might be ahead here. So probably the next important, if not the most important ingredient to severe weather is instability. Instability and shear go hand in hand. You can overcome a relatively stable environment with the increased wind shear, but it's kind of hard to say. But The more unstable your environment is, the greater the severe threat and the greater the tornado threat as well. And this is a big limiting factor on a lot of storm systems, is the lack of instability. So you're probably asking, okay, Ty, so what is instability? It's an unstable atmosphere. And this is measured by our warm air that was forced upward, our ability for our warm air to be forced upward to rise rapidly, or I can't seem to get my words out right now. I'll go ahead and cheat and read this. But instability allows our air that was forced upward by our lifting mechanism to rise rapidly. So this air is considered unstable when the air is warmer or more humid than the air around it. So if you have a little parcel of air that's hotter and more humid rising into air that's a little bit cooler and continuing to rise, that is basically an unstable atmosphere. So this is quantified on the forecast models in another acronym, which is CAPE. I've talked about CAPE a lot on my channel, and this is convective. This is an acronym for convective available potential energy. This is basically considered as thunderstorm juice or thunderstorm food, as Ryan Hall calls it. But there's plenty of ways you can kind of detect CAPE. There's skew-T diagrams, which I pulled up on my channel. But most of the time, I usually will elect to look at a conceptual model that picks up on that, and we'll get into that in a minute. But basically, simply put, the greater the CAPE value, the stronger the thunderstorm, the stronger the updraft, and with this, you can get big hail, you can get really intense, damaging straight line winds from a storm, and of course, tornadoes. And then here's the last ingredient, and also one of the most important as well, and that is moisture. Moisture is the fuel for thunderstorms and needs to be high enough so that way these storms can really thrive. And there's an easy way to measure this. It's something that you've probably seen a bunch of times, not only on my channel, but just from your local weather channel or local news network, and that's dew point. So basically, in order to really measure out dew points, it's relatively simple because it's measured in Fahrenheit just like our regular temperatures. So here's a perfect diagram as to what is more favorable with severe thunderstorm development. Usually anything below 60, the threat isn't that high. It's once you start getting into those mid 60s especially is when you start being concerned. And once you start getting into those 70s, you're in a very ripe environment. I've been in these kinds of environments before, and it's crazy. It's almost unbearable how humid it can be sometimes. It almost feels like you're swimming more than you are walking. It's a funny comparison, but that's how it feels to me personally. But yeah, all four of these ingredients are the key to what forms severe thunderstorms and supercells, and it's these supercells that we often have to look out for tornadoes with. That we often have to look out for the threat of tornadoes. So here's a little diagram of the supercell here. We'll be talking about that more in another video. I just thought I'd show you. But that's what we have. But that's the final result of everything. So now that we've gone over that, let's go ahead and take a look at what a front looks like on a diagram here. Here is the November 4th event actually, which ended up occurring just to the north and east of Dallas, I would say, where we ended up getting a pretty sizable tornado outbreak here. But here's our frontal boundary right here. This is the blue line with the little triangles on it. That's our cold front. Here's our cold air right behind it. And then you see this little pink boundary here. That is a warm area. That is a I've lost my touch on names right now, but that's not a warm front. But this is what helped create the warm sector out ahead of this cold front, which allowed for storms to fire. And that's always one thing that we have to look out for with these kinds of setups, is we have to look for a little warm sector. And that's why I'm having trouble forecasting this storm system that's going on, that's possible around Thanksgiving. It's because I'm trying to figure out if we even have a warm sector to work with, and not all the models are really picking up on it. So it's a little messy right now. But that's what we have going on with that. And then with that warm sector, there's often a moist sector too. You usually won't have one without the other. And this is the moist sector depicted here. Notice it's right around that same area where that frontal boundary is. And then also behind that front, notice that there is an area of dry air loft. This is also important, and we'll talk about that in another video as well, where we can get what's called a capping inversion, which is not to be confused with CAPE, but this can also limit thunderstorm development. This can be a good thing, but it can also turn into the hangman's noose if you aren't careful. If this cap were to break at the wrong time, because these caps can be broken. Like I said, I'll get into that in another video. But let's go ahead and actually look a little bit more in full at the severe weather event around November 4th. So we're going to start out by looking at the jet stream again. So one way to look at the jet stream, and there's two levels that I usually will tend to look at more so than anywhere else, because there's usually 3 levels you can look at, or actually 4, but I usually look at the 500 millibar and 850 millibar region. So this is the high levels of the atmosphere right here, and you can see what's going on here. The winds are always going to be strongest around the 500 millibar region. So here's our depicted area of low pressure right here. You can kind of see it as indicated by this little circular isobar here. And then you can see we have a neutral tilt here in the jet stream. And then we move this along and it starts to go a little bit negative here. Winds really start to scream by this 8th frame here. And then when we look here, when we look at our legend here, if I can get this to move, we're getting close to that 80 to 100 knot frame here. Usually for severe weather, you're looking towards at least about 40 to 60 knots being acceptable for some severe development around the upper levels of the jet stream. But we've more than surpassed that here. We have a very strong jet stream, and of course this would aid in our tornadic development. And then if you look at these little wind barbs here, these little areas right here, this depicts which direction the winds are going in at this particular level of the atmosphere. So keep note of that. We have a little bit of a slight northwesterly flow, and this led to some directional shear along with the speed shear that we already have here. Speed shear is pretty much, in this case, measured by the this legend here. So when you have an 80 to 100 knot jet at about 20 to 30,000 feet, that's usually a sign for trouble. So that's what we were looking at the higher levels of the atmosphere. Let's go ahead and go to the 850 area. All right. So if we look at this, and you can also see how this is drawn in moisture here, because this is the Gulf of Mexico right here. And you can see this is our moist sector right here. If you remember from one of the diagrams I showed just a minute ago. But if you were to go back to that last model here, like you can imagine, okay, so we have this wind barb that was going right here towards the higher levels of the atmosphere. We go to the low levels, and now we're starting to get into like this little bit of an L shape taking place. So basically I'm going to try to simulate this with my cursor. I don't really have the software to put any markings on this, which really irritates me. But think of it like this. Okay, so take one hand, take your left hand for example, and tilt it in this direction right here and just push it forward like that. So just kind of go like that, like this right here, and then take your other hand and try to move it up like this. And the best way to really depict this is to like try to put something like a pencil in your hand and have your hands move in those two different directions. You'll feel the pencil starting to rotate under your hands in a more than likely in a counterclockwise motion. And this is basically what was going on over this area before the thunderstorms started to develop in this region. So next, we're going to go ahead and look at the CAPE values here. This is going to show how unstable the atmosphere was over this region leading up to the event. So here's how we can look at our values here. So this is our mixed layer CAPE, by the way. Mixed layer CAPE is usually the best way to measure CAPE because it measures CAPE at different levels of the atmosphere versus surface CAPE. I mentioned a while back in one of the videos that I kind of liked looking at the surface CAPE more. I was wrong. I'll be the first to tell you that. Because I can only look, because with the surface CAPE, I could only look at what was going on in the surface, not the higher levels of the atmosphere. So it would leave a lot of question marks. So I'm kind of going back on my words here, which is fine because I want to give the right information to you guys. So we always want to try to look at the mixed layer if we can. But anyway, our mixed layer CAPE, we're looking at values that were sitting at above 1,000 to 1,500 joules per kilogram. I actually remember looking at this storm system a few days before everything had unfolded, and I was saying right around this region in particular here was going to be really dangerous. Couldn't have been more right on that, unfortunately. I was kind of hoping I would be wrong. But if we actually looked at a sounding, you can kind of get a better idea of what the CAPEs were doing. And you can kind of see it right here. The average mixed layer CAPE here was 1,208. To put it in perspective for you, when you're looking for a severe weather outbreak, you're looking for CAPE values usually around 1,000 joules per kilogram. So this more than met the mark. And then also if you look at the this little barb here, you can see the directional shear here. And you can also look at it on the surface levels of this QT plot graph, and you can kind of see the changing of directions here at the low to mid levels of the atmosphere. So this environment was more than primed enough to produce tornadoes. And also you can actually see the capping inversion here. So it was unstable in the higher levels of the atmosphere, but there was some warm air aloft that was blocking this region, that was blocking this those air parcels from rising towards the rising from the surface. This of course would break later and allow for severe storms to develop, and we would go from there. So now we've gone over that a little bit, let's go ahead and look at the bulk shear. Bulk shear I don't get into quite as much. I kind of lean more into just looking at the low to mid-level jet or lower and upper level jets to just kind of see what's going on with the atmosphere more so than anything else. But this is an effective tool to kind of get an idea of what our tornadic parameters could be like. Excuse me. So here's our storm system coming in, and we can watch this bulk shear really start to pick up around here. At one point it looks like we have a indice of about 100 right here, which is kind of crazy. But you could see that there's plenty of wind shear around this region. The darker colors usually indicate much stronger wind shear than these lighter colors here, along with the indicated values here. So we move this along, and right around this boundary is where these supercells ended up developing and producing the tornadoes that we would end up seeing all throughout northeastern Texas and into Oklahoma and Arkansas, some of which were violent. And then there's other ways you can also look at stuff too. There's always the significant tornado parameter, which I don't look at much because I can't really because without those other parameters, you don't really always get accurate readings from the significant tornado parameter, so to speak. But the colors here will indicate where the environment is most primed for tornadic activity. So we'll move this along here, and right where you see that red area is where those ingredients really started to come into place. We got 3s and we got 4s in this region here, and this of course is where some of our strongest tornadoes ended up occurring. And of course that went all the way up to a 5, and then once we got later into the evening, parameters started to go away and we just went from that point. So basically that's what happened with the November 4th event. Just a quick rundown, not my best rundown, just kind of doing some of this on the fly. But now that we've gone over that, let's actually talk about some of the stuff that I use, some of the stuff that I'm very familiar with, and we go from there. So for me, the way I depict a area of low pressure, there's 2 ways to do this. You can use this regular precip map here. It's one way, but personally I prefer to use a vorticity map. So it doesn't matter which model really. It kind of does and it doesn't, but I like using both the GFS and the Euro so I can have some models to compare one to the other, and just kind of go the forecast based on what those 2 are doing and see if there's any sort of middle point or common ground between the 2. So this is actually just now starting a new run, so we're gonna have to go back to 18Z. And I actually haven't had a look at the 18Z today, but basically I'm gonna show you a storm system that I'm actually tracking right now, and here it is right here. So this is an area of low pressure that's starting to develop right here. It's the early stages. Move this along, and you see that little dip that's starting to form around this trough here? That's one thing that you always want to look for. That lets you know that that low pressure strengthening, it's starting to dig into the atmosphere. It's gonna this is gonna basically break off a piece of the jet stream here, and this could become a extreme weather maker. And this is kind of and this is a little bit different from the trend I saw a little earlier today. There isn't too much of a warm sector to work with here, so I'm not sure about the severe weather threat with this one. I do think it is possible, but it's kind of hard to pick up on. But with this kind of energy in the atmosphere, there is a warm sector, then oh baby, we could have some big problems here. I'd say maybe further towards the south here, we could have something pop off, but for the most part, I think it's actually looking like it's going to be too cold here. And I bet you're probably wondering, but Ty, how can you tell how cold this is when you aren't even able to look at the temperatures? So you see these lines right here, where you're seeing numbers like 582, 576, 570. These aren't exact indicators of the temperature, but one thing that you can note here is this 540 line. The 540 line is one number that you need to remember, because that is your 32 degree line. Your 32 degree line is anything that's lower than the 540 line is temperatures that are going to be below freezing. Now I'm not super sure as to what these other numbers may mean as far as an exact temperature, but usually what I see from about 570 and onward are usually going to be temperatures above, I'd say 50, 60 degrees for a lot of areas. So as we move this along, we can see this storm is getting a lot colder. And this also may get some snow on the backside of it, along with the inclement weather coming in on the 26th here. So this looks like it could become a big northeastern type of system where we could get some big time snow totals over here towards the Delmarva region and the northeast. And beyond that, we'll watch that head out, but that's one good way to actually indicate lift in the atmosphere is by looking at the upper dynamics here, looking about 20,000 feet into the atmosphere. And then when you see stuff like this is a very clear sign of a strong storm system. You can see the big dip in the trough here. Neutral tilt, by the way, almost trying to go negative. Doesn't quite get there. Almost tries to make the appearance of a cutoff low. I don't know for sure if it does go that route. This part I'm not necessarily an expert on just yet. I'm not super strong when it comes to figuring out cutoff lows, but this has the look of one for sure. But also, once we look into this, we can see our next storm system pop off right here, or try to develop. But it looks like it's mainly going to be a more northerly storm, definitely looking more like a snowstorm than a severe weather threat. And then we just kind of go from there. And then also you can see a little bit of ridging taking effect here around the west, east, and then back toward the west, which could result in some much warmer weather, which could set the stage for a future severe weather event as well. And we aren't going to see that just yet. Not on this model run, at least. So that's one way to look at the upper levels of the atmosphere. Of course, we can also look at the temperatures here, or we can look at the temperature anomaly. The temperature anomaly is really good, and that's a way to look at potential cold fronts, warm fronts, areas of interest. So look at this right here. Here's a little area where we could be looking at temperatures that are above average, below average here. The below average, of course, is going to be more of the blue colors, and the warmer colors are going to be in the red here. So we move this back a ways. And usually this isn't the best way to look at it, but this is always looking at model trends here. Temperatures that are going to be below average, of course, like I said, are in the blue. And when this storm system comes in, we do have a little area that's going to be above average here, right around this region. And then you can start to see this system roll in, just based on this little area here where we have a temperature contrast. That cold air really starts to surge in behind it, and it sneaks in on the south side, which makes it harder to kind of depict if there's going to be a severe weather threat. I'll be looking towards this region, but I'm still not very sold on this just yet. And then of course, as that storm system moves out, that cold air starts to dig in into the east, and then we go from that point. But that's just one of multiple ways. You can also look in the upper dynamics and look at the height anomaly. And it's pretty much the same thing, but you can actually see what our low pressure looks like on here. So I prefer using that more. And basically once we get, okay, we gotta go back a little bit, I forgot. So here's a storm system on November 23rd. Then here's our trough, here's our low pressure right here. Like I said, not a lot of warm air available out ahead of this, so I do think that limits the severe weather potential, at least according to the GFS. Nonetheless, it's still something we have to watch. And then here's our next big system. We'll have to watch that because that looks like it kind of has a trough ejection look to it. And then we just go from there. So that's looking at the higher levels of the atmosphere. And then when you look at the lower levels, here's our 850 millibart region. And we look at the height and wind, and this will show you what your low level jet looks like. We'll move this back, if it'll let me. Uh-oh. Trying not to crash my computer all at the same time because I know this is going to be a long video. Okay, so we're back to the 23rd. And with this system, our low level jet doesn't look super impressive. At least not until the 26th. We may have to watch this region for potential severe weather according to the GFS. But if you look on other models, this will probably show a different picture, so we got to be careful. We got to be careful with making forecasts on this because model discrepancy can be your biggest enemy. But yeah, that's what we have going on there. So that's looking at the low level jet, and we can look at the high level jet right here by looking at 500 millibar height and wind, but that's not really pulled up on this one. I think you could do so. You think you could look at it on the Pivotal Weather website there. But essentially, those are the main things that we look at here. And then, of course, the last thing, it's pretty self-explanatory on how to find moisture. You just look at the dew points 2 meters above the atmosphere. That's about at the surface level. And here's another reason why I'm not super concerned about that potential storm system bringing in a lot of severe weather. It's because the moisture return from the Gulf just isn't quite there. I mean, there is some return. You can see that here. But I just don't think that storm system will mature well enough in time to really become a big factor here. Maybe on the 26th we'll have to watch this region, or in the night of the 25th we'll have to watch around the southeast for some severe weather. But it looks like it's going to be relatively limited. And then that storm system's out of here. Okay, so last thing that we will look at here is the precipitation here. This is another way to kind of depict the storm mode. And you can also, and this is probably the best way you could look at convection, or sometimes as we call in the weather community, crapvection. Crapvection is important because this can also hinder thunderstorm development, but that's another video to talk about. That's another video for another day. I know this has been a long one because now I'm starting to really stumble over my words here. But GFS does have this hot on something by Friday night, not Friday night, but late Thanksgiving night into early Black Friday. And this system does look like it has a little bit of potential to produce some severe weather, maybe a line of storms. And then on the backside of it, we could potentially see a push of snow. Severe weather threat looks relatively limited, and there's a very small window for it as well. Plus, this system is moving quickly, very progressive, if you will. And progressive systems often limit severe potential as well. We'll talk a little bit more about that in another video as well. But that's another way to look at low pressure centers, look at convection, look at moisture returns, is the precip map itself. You can be pretty basic, but if you want to get into the more advanced stuff, I figured I'd show that up to you on this video here. But I know this has been a long one. I actually want to look and see how long it has been. It's been almost 40 minutes. It's my longest video yet. Hope you guys appreciate it. So I'm pretty pooped. You can see the time down there in the bottom as well. But yeah, this is the end of the video here. I've clicked the sounding by mistake. But I hope you guys enjoyed it. If you did, definitely drop a like. Leave a comment as far as the potential name for this playlist is concerned. I think I found it, but just in case I go back on it, a suggestion in the comment wouldn't hurt. Excuse me. But of course, share this video to anyone that's interested in weather. I'm not a pro at explaining these things. I'm not a great speaker, but I figured I'd just try my hand at it. We'll be doing more videos like this in the future. So if you enjoyed this one, also subscribe if you haven't already. But enough rambling from me. I gotta go to bed and get ready for work in the morning. But this has been Tired Metalhead Weatherman. You guys have a good one. I will see you guys next time.